So I want to do a quick lesson here. It involves Snell's law, but it involves a certain application of Snell's law that's kind of interesting. So I wanted to show you it. Before we do that, though, I would like to address one of the questions on the quiz from last week. The question asked, when light enters a new medium, um, let's see here, where am I? When light enters new medium from along the normal, which way does the light bend? And what that was testing was your understanding of the two key pieces that need to be present in order for light to bend. Number one, light has to go from one medium to another. It has to enter a new medium so that its speed changes. It either speeds up or slows down. And number two, it has to do that at an angle. And as you can see here, I'm going to rotate this over here. In all these cases, the light is bending. You can see as it enters the water down here, it's bending towards the normal because it's slowing down. But when we get to the normal, it doesn't bend. You can see that it goes straight into the new medium. It comes in along this dashed line, the normal, and it continues along this dashed line, the normal. If I go past, it won't let me go past, but if I'm a little bit short, it bends towards the normal. But if I'm at the normal, there is no normal to bend towards, or I should say it's already along the normal, so it can't bend towards itself. So the correct answer to that question was light does not bend. A couple of you got that correct. Many of you did not. So that's just something to think about. So as we are moving along here, I want to show you a very interesting and intriguing, I think, case. In order to do this, I'm going to need to switch. I'm going to need to put the water above the air because of the way this works. There's water and water. You can see because it doesn't, even though it's coming in at an angle, there's no change in medium, so it doesn't bend. But when I go from water to air, now I know this is unrealistic, right? Because you can't have water over air, but it's just the way the simulation works. So work with me. So when you go from water to air, you can see that the angle gets larger because when light goes into air, it speeds up and bends away from the normal. Now, if I bring this protractor in over here, I can take a look at these angles, and I can see that this angle up here is about 25 degrees, and this one's a little over 30, which makes sense. It bends away from the normal. If I increase this angle a little bit to say about 40 degrees, you can see this one also increases, but it increases more. It's now up around 55, 57 degrees. So again, the angle here is smaller, so it bends away from the normal. All right. And as this angle continues to increase, you can see this one gets bigger and bigger. Now, some of you are probably thinking to yourself, huh, at some point, something weird's going to happen here. And you're right. At some point, something weird is going to happen. And I'll try and go slowly to that point so you can see the weird thing about to happen and then finally happening. So as this angle up here, you can see it's beyond 40, it's almost to 50, okay? As this angle gets closer and closer to a particular point, watch the light beam down here. Watch the light beam down here in air, all right? As it bends more and more away from the normal, at some point it disappears. And you'll notice this angle is now at 50 degrees, and there's no more light ray down here. When I was at 48 degrees even, there was a light ray. But when I'm at 50 degrees, there is no light ray. So somewhere between here, 50 degrees, no light ray, and here, 48 degrees, a light ray down here in the air, somewhere in between there, something important happens. The light bends so much that you cannot see it in the new medium. And this thing has a name for it. It's called total internal reflection. In other words, the light ray stays inside the water. Now, again, this is a weird perspective because the water is over the air, and that can't really happen in real life. But if you flip it upside down, if you go ahead and turn your Chromebook upside down, it might make more sense. You've got a light ray trying to get out of the water into the air, and it can't. At a certain angle, it just can't get out. The light ray is reflected. This is the reflected ray, but it's reflected inside the water. It does not get out of the water into the air. At smaller angles, it does. No problem. There it is. It bends away from the normal, but it gets out. But at some angle, and we have a name for that angle, as you might imagine, we call it the critical angle. At a particular critical angle, you can see anything bigger than that, the light ray does not get out. Smaller than the critical angle, the light ray gets out. Bigger than the critical angle, the light ray does not get out of the water. So the next video I'm going to post today is going to be a math problem where we solve Snell's law for that critical angle. We try to figure out exactly where this occurs. And this simulation gives us a pretty good idea, right? 50 degrees doesn't get out. 47, 48 degrees does get out. So you got a pretty good guess of what that critical angle is going to be about. But I'm going to show you how we use Snell's law to calculate exactly what that critical angle is. And it's different, right? This is water and air. It would be different if we were in glass and air. It would be different if we were in diamond and air. So I'm going to stop the video now. I'm going to make another video where I show you the calculation, but I'm going to let you play with this, right? This simulation is in your folder. You can access the link to this simulation in your folder, and you can do this all you want, do all the calculations you want to practice critical angles. You can change this up from water to glass to mystery substance A and mystery substance B. You can customize the substance to have an index of refraction, whatever you want it to be. All right. But I'll let you do that on your own. All right. And the next video, we'll see how you do this calculation so we know exactly what that critical angle is. All right. Thanks.